Hi everyone, today we're going to be talking about an interesting topic which is elliptic curve cryptography. So this project is done and presented by myself, Mehalli, and Oumaima Elkhedar, and also Douae Elfatihi. Concerning the structure of our presentation, we will start with a short overviews about the SSE. After that, we will present some algorithms like elliptic curve Diffie Hellman, elliptic curve integrated encryption scheme, and the elliptic curve digital signature algorithm. Then we will present some applications domain and a comparison study between SSE and RSA. And finally, we will show you a short demonstration of our code and also some future points about this crypto system. So what we have to know here is that elliptic curve cryptography is a crypto system, which means that it manages key exchange and unique key generation, also the encryption and decryption features, also the signature and the certifications. So also it is used in computer science domain since 2005, but it is also known even before since 1985 in mathematics. It is an asymmetric cryptography while it uses public and private keys to exchange the keys. It has a strong trapdoor function, which is a very hard mathematical problem that we will see later. So it is the most used and powerful standard while it is used in critical domains like in crypto money, like in blockchain systems or in web browser system like in Tor, and also to protect state private file or top secret files like in NSA or KGB. Also, what we have to know is that it's not all roses in the world of elliptic curve cryptography, while it has some downsides, like in dual elliptic curve deterministic random bit generator, which is a generator system of a large number, which will be used in the private key. So it is discovered that this system, this large number could be predicted by, let's say, all black hat hackers if they have the private key. Also, another case is an elliptic curve digital signature algorithm, which has some drawbacks compared to the RSA in some way that it required more entropy. So without proper randomness, the private key could be easily revealed. So here we represent some graphical characteristic of SSE. So the function of SSE is here. We have y squared equal to x cubed plus ax plus b related to the constraint for a cubed plus 27b squared must not be equal to 0. So here we represent some operations like addition and multiplication. So for the addition, we will start with 2 points P and R. We will draw the line through these 2 points, and the reflection of the intersection here will be the sum of P and R. And with the same process, we can also process the multiplication or the dotting point of starting point here P. We will draw the tangent over this point, and in the same way, the reflection of the intersection of the curve will be the 2p. The third one and the final one shows that we can perform as many dotting operation as we want. So for example, here, if we calculate the 3p, we have just to draw the line throughout p and 2p here, which is q, and we will take the reflection, which could be here. So this section is very important to understand the next section, which is the trapdoor function. So here we have to choose the A and B parameters that we saw previously here, and choose a P point, starting P points. And after that here, we have to make as many dotting operations, and we will get a P prime. So the elliptic curve the elliptic curve discrete logarithm problem says that given these 2 points, the starting one P and P prime, it is impossible mathematically to find the n times dot n operations. So this is the basic security of elliptic curve cryptography. Now I let my friends continue with the SSC algorithms. Thank you.
Thank you, Nassim. So in this part, we will talk about the elliptical curve algorithm. The first one, it's ECDH, which is the elliptical curve Diffie Hellman protocol. It's a secret key generation protocol between two distance parties, Bob and Alice. We'll take the famous ones. So in order to exchange their public key, they will follow these steps. The first thing, it's Alice will generate a random key, a random private key, named DA, and takes a point on the elliptical key called generator G, and then determines her public key by the way of computing the multiplication between her own private key and the generator, and then pass this public key to Bob. Likewise, Bob will also generate a secret key and then compute a public key and pass it to Alice. So after obtaining the public key from Alice, Bob will compute this value, which is the multiplication between his own, which is the multiplication between his own private key and the public key of Alice, and we'll get the multiplication between the three elements: the public key, the private key of Alice, the private key of his own, and the generator. And Alice will do the same, and she will get the same result. So here is the common shared key named S, which is the multiplication between the two private keys and the generator point. After this, we will talk about the elliptical curve integrated encryption schema. So this schema, it's an hybrid schema that uses a public key system to transport a session key for use by a symmetric cipher. So in this protocol, a Diffie-Hellman shared secret is used, as we explained before this. So to drive two symmetric keys, key 1 and key 2. The key 1 is used to encrypt the plain text using a symmetric key cipher, and the key 2 is used to authenticate the resulting cipher. So this protocol follow the three cryptographic primitive. The first one is KDF. It's a key derivation function. It's constructed from a hash function, and we have the ENC, which is the encryption function for symmetric key encryption, and then we have the DES, which is the decryption function, and finally the MAC, which is the message authentication code algorithm. So this is the concept of ECIES. And then we will talk about elliptical curve digital signature algorithm. So after exchanging encryption key, ensuring that the integration and the authenticity of the communication is a fatal step in the fundamental phase requires user to use some digital signature schema. So elliptical curve cryptography is able to provide the same level of security as RSA. So it guarantees two things. The first thing, it's guarantee a unique and replaceable signature for each private and public key generation, and also it's guarantee the practical impossibility of forging digital signature due to the computing power required for this. So the ECDSA, it follow three pillar. The first one is the private key, which is generated randomly. The public key, which is calculated by the generator, and the private key in order to be a shared key, and then the signature, which is a number that proves that a signature operation has been performed in a good way. So briefly, the ECDSA is done in two phases. The first one, it verify the public key, and then it verify the private key. Now we will talk about the elliptical curve application domains with my colleague Douae. I'll let her to talk.
Now we're going to talk about ECC applications domain. So ECC has many domains application due to its robustness and popularity encryption. It has like the possibility of doing digital signature, pseudo-random generator, and other tasks. Those are major application field of it. It actually varies from traditional to modern application. The most relevant one are National Security Agency for top secret files, smart grid. We have also vehicular communication, Bitcoin, ad hoc network, and so on and so forth. ECC actually is the new replacement or the successor of RSA, which is very limited in processing time and key encryption size, even though computing power resources are increasing. In the following, we present the difference between those two crypto systems. So when it comes to encryption of QR codes, authentication for one-time password, for example, the first figure on the left, this one, basically represents and provides information about an example of time processing. And as you can see, for ECDH, it is more faster than RSA. For the second, third, and fourth one, they represent how faster RSA keys increases in the size compared to ECC, having the same level of security, which explain why ECC uses less computational time to process these keys. Although RSA is well established and based on the difficulty of factoring large integers, its scalability is not optimal. While ECC do need some special adjustment to performs, it relies on detecting the separate logarithm of a random elliptical curve, yet it uses a shorter key, and this shorter key encryption, they are so strong and so far more better than using RSA long keys. It needs a smaller certification size, and it is much harder to crack ECC than to crack RSA. All of those elements do make ECC the new successor for RSA in the future. After this comparison, ECC seems to have better potential, and it does seem very promising as a crypto system. Now we're going to pass to the last part, which is the conclusion.
Okay, so for this, concerning this demonstration section, we will show you our implementation results concerning two algorithms, which are elliptic curve Diffie and the elliptic curve integrated encryption scheme. So here we implemented two classes, person 1 and person 2, which simulate a conversation between these two persons. So if we launch the first one, it will wait for the connection of the second one. And after the connection, they exchange the shared key to calculate the unique key used for the symmetric encryption and decryption. So here, for example, Smail sent this key to Agnès, and vice versa. Agnès also sent its shared key to Smail. So the shared key is this one, calculated with the Diffie method. And here now Smail can send messages to Agnès, for example, here Agnès. So Agnès will receive all this encrypted message, and after the decryption, she got this message. So it's the right message, and also she can send a message, and in the same way, Smile received this encrypted message, and after decryption, it will say this one, etc. So now we will present for you the future points concerning the elliptic curve cryptography. Thank you.
So in this part, we'll talk about the elliptical curve cryptography future. Experts say that the RSA and ECDH could be broken within 5 to 10 years, leaving ECC as the only reasonable alternative. And it will be supported by all modern browsers. All certificates authorities will offer just elliptical curve certification. And the most promising thing about the elliptical curve cryptography, that the quantum computers will be the key element for solving the ECDLP problem. So this is all about our subject, which is the elliptical curve cryptography. Thank you so much for your attention.